Hi, everybody, and thank you for joining us today for our Insulation Intel webinar, Insulating Chilled Water Systems. My name is Kim Melton, and I'm going to be your moderator for today's presentation. Before we dive into introductions, I do want to go over a few logistics. First and foremost is many of us are still working remotely, so if we have any technical difficulties today, we'll pause the webinar for about 5 minutes to see if we can sort them out. If we cannot sort it out in that time frame, we're going to cancel today's webinar and we'll send you a recording of it for you to watch on demand at your leisure. But hopefully we don't run into any technical problems today. As you know, we will be concluding today's webinar with a live Q&A with your host. And if you'd like to submit questions, you can do that via the Q&A feature, and that should be available on the right side of your screen. Now, if you don't see it to the right of your screen, look across the center bottom of your screen. You'll see a series of circular icons. There's one with a question mark and a box. If you click on that icon, it will open the dialog box that allows you to submit questions during the presentation, and we will answer those live at the end of the broadcast today. Secondly, this webinar is for educational purposes only and shouldn't be used as a substitute for professional engineering design, consultation, or documentation that might be required by building codes, contracts, or applicable laws. So if you have any questions after the webinar, you can refer to the specific application guidelines and instructions located on the product sections of our website. Finally, we're going to conclude today's webinar with a survey, and this is your opportunity to provide us with feedback on how we did today. You can ask any additional questions you might have about the topic of the webinar or even suggest future topics for webinars you'd like to see. Now, this survey is part of how we deliver the JAM experience to you, and the JAM experience is based on 4 pillars of the JAM culture, and those are listed in the bottom left corner of the slide. And we believe it's critical to make sure that we hear and understand and respond to your needs in order to deliver the best interaction to you. And we offer webinars like this one to educate the market and offer a tool and a resource for you and your business. But that's not just a one-way street. Your feedback is a key component to helping us evolve to better meet your needs. So if you have any comments or suggestions as to how we can better accomplish this, or even if you feel like we may have missed the mark today, we'd encourage you to fill out the survey, and we'll use your feedback to improve our webinars and provide the information that has the most value to you in future webinars. Now, we're also frequently asked whether we send out these presentations upon their conclusion. We don't actually send out the presentation of itself, but we do post a recording of it online for you to watch at your leisure or share with your colleagues. And this ensures that you can have the presentation within its full context. Now, when this is live on our website, we will send an email to you. So with that, I'm going to hand it over to Meredith Westerdale and Kathi Coyle to introduce themselves. And Kathi, why don't you go ahead and kick us off?
Well, hello, everybody. Thanks so much for joining us today. I'm Kathi Coyle, and I'm the Business Development Manager in the Western region of the Industrial Insulation Products Group of Johns Manville. I've worked in the insulation industry for just a little over 10 years, and I'm excited to be joining Meredith to talk with you today about chilled water systems.
And hello, everyone. My name is Meredith Westerdale. I am the Mechanical Insulation Product Manager here at Johns Manville. The products that I have responsibility over are fiberglass pipe insulation, fiberglass boards, and PVC covers. We're going to start the presentation with an introduction to some of the concepts that are critical for understanding how and why to insulate chilled water systems. So we'll start with a quick primer on heat and moisture. As we all know, heat wants to move from a high temperature state to a low temperature state, and the purpose of insulation is to slow that transfer of heat. The way that we measure that is thermal conductivity, or the K value. The lower the K value, the better the insulation. We're going to be talking about K value in more detail later in the presentation. Water vapor is very similar conceptually. It wants to move from an area of high pressure to low pressure. And the ability of water vapor to move through a material is measured in perms. For a chilled water system, properly managing heat transfer and moisture migration is critical to its success. Now we'll take a closer look at measuring and managing moisture flow. Again, the flow of moisture is measured in perms, which is essentially the amount of water vapor that can pass through a given area of material over a period of time, assuming a static vapor pressure on either side of the material. Vapor retarders are intended to limit the flow of moisture, so they're pretty intuitively named. For vapor retarders used on a chilled water system, we're looking for a perm rating of 0.02 or better. Again, the lower the perm, the less moisture flow. We're going to take a more in-depth look at vapor retarders later in the presentation. Meanwhile, let's take a look at some different examples of water vapor pressure. Water vapor pressure is a combination of temperature and relative humidity. If we were also fortunate to be living in a tropical paradise right now, we would be in an environment with a water vapor pressure likely over 1. Speaking for myself, I'm in an environment more similar to what you see in the middle, where it's probably somewhere around 70 degrees with 50% relative humidity. It should be easier to manage moisture flow in this environment, but there's still moisture drive, or there's still a measure of water vapor pressure, even if it's less than that of the tropical paradise. The same is true for the air next to a chilled water system. Although the temperature is much lower, and so is the water vapor pressure, there's still moisture drive. So it's critical that we manage that with a vapor retarder. It's going to protect the efficiency of the system as well as to prevent condensation. Let's get into the essentials of insulating chilled water systems. It helps to start with an understanding of why we want to insulate a chilled water system. A primary reason is condensation control. As warmer air comes into contact with pipes that have chilled water running through them, those pipes will condensate, just like your glass of ice water does on a summer day. There's several reasons why you don't want your pipes to condensate. You might create a slip hazard from dripping pipes in your building. You might damage the building materials below the pipes, or you may create the opportunity for your pipes to rust as they're continuously exposed to moisture. It's also just as important to insulate pipes if you have the potential for the opposite. That is, much colder air coming into contact with your system so that you are preventing frozen pipes. Insulation also helps to bring down the energy demand on the system as it helps to better regulate the temperature and keep the system more efficient. That means savings for the building owner in terms of energy use and cost. Using less energy is not only better from a cost-saving standpoint, but it's also better for the environment. So in summary, there are many reasons to insulate a chilled water system from the standpoint of safety, process control, efficiency, energy and cost savings, and environmental impact. Now that we've covered why to insulate, let's take a look at some of the design considerations of insulating chilled water systems. These are the physical aspects that you need to take into account as you determine how you're going to insulate your chilled water system. One of the most basic and fundamental concepts is thermal performance. That is, making sure that you have the right amount of thickness of insulation to appropriately control heat gain and condensation. Some references to help with that are ASHRAE 90.1 and ASTM C680. On the fiberglass side, which again is my area of expertise, we would recommend the NAMA 3E Plus tool for use in determining your proper insulation thickness. Another consideration is vapor retarder and system integrity, essentially making sure the right approach is used to properly seal the system. Components like vapor retarders, mastics, tape, and sealant are critical to completing a sealed system and ensuring system integrity. The location, service conditions, and spacing constraints of the system are also important to consider. Is the system going to be in an area of high traffic where it may be prone to abuse? If so, a protective jacketing like metal or PVC might be considered. Spacing constraints are also important to consider. That is, how much space is there in between the runs of pipe may actually determine what type of insulation material can be used. Different materials have different insulating performance at different thicknesses, and we'll talk a little bit more about that later on. You also want to make sure to use an experienced and knowledgeable insulation contractor, and I cannot stress this point enough. The contractor needs to be familiar with the materials that are being used and how to properly install them. Finally, following a quality specification is also something to consider. We recommend following the manufacturer's installation guide for your material of choice. I mentioned that condensation control is a key reason for why to insulate a chilled water system. In order to properly control condensation, you need to make sure the surface temperature of the insulation on the chilled water system is going to stay above the dew point. And that's determined by the ambient air temperature as well as how much moisture or humidity is in the air. It's also critical that the system is tightly sealed. Again, mastic, tapes, and other sealants are important to completing a sealed system. It's also worth noting the 0.02 perm reading for vapor retarders is just as important for other components like mastic. You also need to consider what type of insulation material you're using relative to the environment of your application. The amount of humidity where the chilled water system is installed may help determine what types of materials are used. And I'll pass it over to Kathi, where she'll cover how to determine insulation thickness in more detail.
Thanks, Meredith. One of the key design considerations is limiting heat gain into the chilled water pipe, and that is achieving a certain energy efficiency. The amount of insulation required to accomplish that desired energy efficiency is governed by the energy codes, which in the U.S. are under the IECC, or International Energy Conservation Code, or the ASHRAE 90.1 standard. Fortunately for pipe insulation used in commercial buildings, these two codes have exactly the same requirements. The table on this slide is taken from the current 2018 edition of the IECC, but the ASHRAE 90.1 as mentioned, that standard has the exact same requirements. This table of required pipe insulation thicknesses has different rows that apply to the entire possible range of pipe temperatures, and then a number of columns that cover all the pipe sizes. In addition, the table, as published in the codes, is designed around insulation with a specific thermal conductivity as shown. This happens to be the normal range for glass fiber. For insulation materials with substantially better, or that is a lower thermal conductivity, such as Trimer PIR, or a substantially worse thermal conductivity, such as cellular glass or elastomeric rubber, there is a calculation procedure in the table footnotes used to modify this table to yield thickness requirements specific to these better or worse insulating materials. JM would always be happy to discuss this with you further and create a custom table for any of your needs. It's important to note that this code table is only applicable for energy efficiency. It does not address condensation control, which is an equally important requirement, but is a different calculation and is not required by the code. We'll discuss the required thicknesses for all key chilled water insulation materials later in the webinar, but for now, just be aware that the maximum required insulation thicknesses occur at the largest pipe sizes and in the coldest pipe temperatures. In addition, chilled water applications, code required insulation thicknesses for Trimer PIR and glass fiber never exceed 1.5 inches, and thickness required for condensation control very rarely exceeds 1.5 inches. Water is one of, if not the greatest threat to proper functioning of an insulation system. Water is one of the key factors necessary for mold to grow, so water intrusion into and even onto the outer surface of the insulation system can lead to mold growth. Additionally, other surfaces of the insulation system, when water is present, can also be at risk. Mold growth is very costly to correct, and if left unaddressed, it can lead to building-related illnesses. Water is a very poor insulator, so if water enters an insulation system, it will cause the insulation to become more thermally conductive and compromise the thermal performance of the insulation system. This creates a problematic cycle, wherein water entry into the insulation hurts its insulating ability, which leads to greater amount or likelihood of surface condensation, which in turn may lead to further water intrusion into the insulation, and the cycle continues until the insulation system is completely waterlogged and no longer functions as an insulation. Now let's take a look at understanding flame and smoke ratings. When discussing commercial building chilled water pipe insulation, it's important to understand the required flammability performance. Flammability of pipe insulation in a commercial building is governed in the U.S. by the IMC and adopted by local jurisdictions and interpreted by local authorities that may have jurisdiction. Examples of commercial buildings to which these code-mandated flammability requirements apply include office buildings, large apartment or condo buildings, all tall buildings, schools, museums, hospitals, and government buildings. In the IMC, the flammability of pipe insulation is measured using the ASTM E84 or tunnel test that generates two properties, a flame spread index and a smoke developed index, often abbreviated as FS/SD, as you can see in that last bullet point. In the IMC, the flame/smoke development of a 2550 rating is technically only required when the pipe is located inside of a plenum. Pipe insulation located outside of a plenum only has to meet an E84 flame/smoke of less than or equal to 25450, which is also known as Class A or Class 1. It's important to note that plenums are typically a very small part of the building, and only a small fraction of the pipe insulation is located within a plenum. Most pipe and pipe installations will not be located in a plenum and would only require a flame/smoke of less than or equal to 25450. Some buildings, such as modern hospitals, use fully ducted HVAC systems to prevent the spread of germs, so they are likely to contain no plenums at all. However, given these facts, most specifiers prefer to require all pipe insulation inside a commercial building meet flame and smoke of 2550. This might be preferred to avoid any chance of an authority that has jurisdiction of incorrectly requiring a 2550 performance, or perhaps to avoid the installer making a mistake and putting the wrong insulation in a plenum. Whatever the reason is, it's our experience that most specifiers require in their specs that pipe insulation in a commercial building meet the flame and smoke of 2550 even where the code does not require this. It should be noted, however, that pipe insulation located outdoors, including rooftops or in industrial facilities, usually are not governed by the IMC. So these usually do not need to meet a flame and smoke of less than or equal to 2550. Of course, a specifier in these facilities may still decide to put a flammability requirement into the spec, but rarely is it a 2550 requirement. And now I'd like to turn it back over to Meredith.
Thanks, Kathi. So now we're getting into my favorite part of the presentation. As a product person, I'm excited to talk about the different types of materials that can be used to insulate chilled water systems. So we're going to be reviewing 5 different types of materials, and JM offers 3 of them, which you can see along the top. There's fiberglass pipe insulation, like JM's Microlock HP products. Fiberglass is a sand-based material. The pipe insulation sections come pre-formed, pre-split, and with a factory-installed vapor retarder. It's also worth noting that fiberglass is sold with butt strips, which are used to seal the seams between installed sections and are a key part to completing a sealed system. There's also polyiso, like JM's Trimer 2550, which is a rigid plastic foam. Polyiso is manufactured as bunt stock, essentially big blocks that are then fabricated into pipe sections and fittings. There's also phenolic foam, like JM's Trimer Supercell Phenolic. This is also a rigid foam that is initially manufactured as bunt stock and then later fabricated into sections and fittings. 2 other types of insulation that JM does not offer are elastomeric rubber, which is a flexible insulation manufactured in tubes and rolls, and cellular glass, which is a rigid insulation. It's actually manufactured in blocks. The blocks are glued together and then can be fabricated into pipe sections and fittings. Next, we're going to review some of the benefits and considerations of each of these materials. Our goal is to provide some background to the differences between these unique materials and why they're used. We'll also review some basic product attributes along the way, like K value, the perm rating of the associated vapor retarders, and whether the product is open cell or closed cell. As a quick refresher, K value is a measure of thermal conductivity, and the lower the K value, the better insulating performance of the material. So we'll start with fiberglass, which has a K value of 0.23. Fiberglass pipe insulation typically comes with either an ASJ or a poly-coated ASJ vapor retarder. The ASJ, like in our Microlock HP pipe insulation, has a perm rating of 0.02, and the poly-coated ASJ vapor retarder, like in our Microlock HP Ultra, is slightly better at 0.01. Fiberglass is an open cell insulation, meaning the air pockets are not fully sealed off like in closed cell insulation. We'll talk a little bit more about that in a bit. The benefits of fiberglass are that it is a relatively low-cost material. It's also widely used amongst insulation contractors, which is important because there's widespread familiarity with proper installation practices. Fiberglass is also widely available through distribution, so it's very accessible for insulators to purchase. The poly-coated ASJ also provides additional moisture protection. This vapor retarder helps shed intermittent moisture that might occur on a job site if the building has not yet been fully sealed up. Fiberglass meets 2550 flame smoke spread at all thicknesses, and as I've mentioned, the vapor retarder comes factory installed, so no additional installation step is needed. The K value is considered good at 0.23. In terms of thermal conductivity, fiberglass is essentially in the middle of the pack versus the other materials that we'll be reviewing. So we've covered the benefits of fiberglass, so let's keep a balanced perspective and review some other considerations. Fiberglass is an open cell insulation, meaning it's critical that the vapor retarder remains intact. If it's damaged, moisture will penetrate the insulation and it will lose its insulating value. This will also create the opportunity for mold to grow, so it's very important that vapor retarder integrity is maintained. If fiberglass insulation gets wet, it should be replaced. Proper installation practices are critical to the success of fiberglass insulation on a chilled water system. Fortunately, fiberglass is very commonly used amongst insulation installers, as I've already mentioned. So now I'll hand it back over to Kathi to review some other insulation materials.
Thanks, Meredith. The next insulation material we will discuss is Trimer Polyisocyanurate from Johns Manville. As polyisocyanurate is quite a mouthful, this material is usually abbreviated as PIR, although some in the industry incorrectly refer to it as urethane. The Trimer PIR product that we'll be discussing for use in commercial building chilled water is named Trimer 2550. This is a recently acquired product for JM, and it came with the December 2019 acquisition of ITW Insulation Systems. This product is a closed cell product, and as you can see in the second bullet point, it has a thermal conductivity of 0.19 at 75 degrees. This compares quite favorably to the other materials that we have or will discuss, which have thermal conductivities ranging from 0.18 to 0.31. The Trimer 2550, being a closed cell rigid foam insulation, also has a good compressive strength of 24 psi. It's resistant to both liquid water and water vapor. However, it still requires the use of a high-quality continuous vapor retarder in cold applications such as on chilled water pipe. Like fiberglass, the vapor retarder usually comes factory applied to the surface of the Trimer PIR, although this vapor retarder is applied by the fabricator, not the insulation manufacturer. This really isn't an important distinction since the contractor still buys the pipe insulation half shells ready to install. In fact, the application of the vapor retarder by the fabricator is usually a benefit for two reasons. First, the contractor could procure the Trimer 2550 PIR insulation with no vapor retarder if that was of benefit in a particular application. Second, and more importantly, Trimer 2550 PIR can have a wide variety of vapor retarders factory applied to it. These include ASJ, poly-coated ASJ, JM Sarin XCX vapor retarder, which we'll talk about later, and a variety of other high-performance vapor retarders, such as mylar, aluminum mylar. Vapor retarder flexibility is really an important benefit for Trimer PIR, and it can be used with a high-performance vapor retarder like our Sarin XDX, as mentioned, in high humidity, non-climate controlled environments, such as outdoors or in machine rooms. Trimer and the various vapor retarders mentioned meet the important flammability requirement. That is, they all have the ASTM E84 flame/smoke rating of less than or equal to 2550. Trimer 2550 meets this 2550 rating at thicknesses up to 1.5 inches, and this thickness is adequate for code compliance in virtually all indoor condensation control applications where a less than or equal to 2550 performance would be required. It's also worth noting, as you can see in the last bullet point, that JM's Trimer 2550 PR is the only CFC and HCFC-free PIR insulation that meets this 2550 rating. Some considerations for Trimer 2550 is that it is a higher cost material than fiberglass, but it is a lower cost than any of the other materials that we're discussing, including phenolic, cellular glass, and elastomeric rubber. In particular, Trimer 2550 is much lower in material costs and total installed costs than cellular glass. Trimer 2550 is manufactured in large buns and requires fabrication into the necessary pipe shell shapes by a qualified fabricator. While this is definitely a necessary step, it's not a particularly burdensome one, as JM has a network of over 50 highly qualified fabricators located across North America. Now let's talk about phenolic foam and its benefits. This is the last of the insulation materials that we'll be discussing. This is not a very common material, and the name of the phenolic foam material that JM sells is Trimer Supercell Phenolic. Like the Trimer 2550 PIR, this product was also recently acquired by JM in the December 2019 acquisition of ITW Insulation Systems. Phenolic pipe insulation has the lowest, and that is the best, insulating ability of any of the materials we'll discuss. Specifically, you can see, as listed in the second bullet point, that it has a thermal conductivity of 0.18 at 75 degrees F. Phenolic insulation has many of the characteristics that we previously talked about with the Trimer PIR, in that it is a closed cell, rigid foam insulation and has a good compressive strength of 33 psi. It is resistant to both liquid water and water vapor, and like PIR, it requires the use of a high-quality continuous vapor retarder in cold applications such as chilled water, and it comes from the fabricator with this vapor retarder already applied. Trimer Supercell Phenolic insulation meets the usually required 2550 flame and smoke rating at thicknesses up to 3 inches. And this thickness is more than adequate for code compliance and all indoor condensation control applications where a less than or equal to 2550 performance would be required. The key benefit of phenolic insulation is in rare circumstances as compared to the Trimer 2550, where a thickness is required of more than 1.5 inches, it can meet that 2550 code up to 3 inches. And like Trimer 2550 PIR, phenolic insulation is also CFC and HCFC free. Now let's talk about some of the considerations. The material cost of phenolic is higher than that of Trimer PIR and also of the products that Meredith has been promoting and also selling during her time in the field. So it would typically only be used where the very low or good flammability performance is needed at thicknesses greater than 1.5 inches. Phenolic is cut into necessary shapes by the same network of fabricators previously mentioned and is also widely available in North America. Phenolic is the least used chilled water pipe insulation product of those being discussed today. And now I'd like to turn it back over to Meredith.
Thanks, Kathi. We're going to take a look at some of the products outside of JM's offering, starting with cellular glass. Cellular glass, as Kathi has mentioned, does have the highest K value of all the materials at 0.31. It is typically installed without a vapor retarder because the material itself is zero perm. The fact that cellular glass is zero perm is one of its primary benefits and makes it pretty unique. None of the other materials we're reviewing have that quality. Cellular glass is also closed cell. It's a rigid material with good compressive strength and meets 2550 flame smoke at all thicknesses. There are some other important aspects to keep in mind for cellular glass. I mentioned it has the highest K value, or the poorest thermal conductivity of all the materials we're reviewing. And that means you need thicker insulation to achieve similar insulating performance to other materials with lower K values. Needing greater thickness adds to material cost and can be a concern if there are spacing constraints in the application. Additionally, although the material is zero perm, all the joints and seams must be sealed with a vapor retarding sealant to maintain that quality through the whole system. Cellular glass also requires fabrication and can be crumbly when handling it, making it difficult to fabricate and install. Also, it's made available in shorter pieces relative to the other materials, which means more joints and sections to install and seal. From a material cost standpoint, cellular glass is relatively the highest of all the materials that we're looking at. The final insulation material we will review is elastomeric rubber. With a K value of 0.245 to 0.28, its thermal conductivity is not as good as fiberglass, but not as poor as cellular glass. Elastomeric rubber tends to be installed without a vapor retarder, which would not be recommended on a chilled water system. The sections and seams would also need to be sealed. In terms of benefits, it is a closed cell insulation, and unlike all the other materials we've reviewed, it's flexible, which makes it attractive for installing on any piping that is not entirely straight. Elastomeric rubber is also widely available through distribution. While elastomeric rubber is typically installed without a vapor retarder, and that might be viewed as a positive, elastomeric rubber by itself does not meet the perm rating that would be required on a chilled water system, which again is 0.02 or lower. Again, all the joints and seams would need to be sealed when installed on a chilled water system, which does add time to the installation process. The material cost of elastomeric rubber tends to be relatively higher than fiberglass. This is especially true for sizes with greater thicknesses. Additionally, elastomeric rubber does not meet 2550 flame smoke rating at thicknesses greater than 2 inches. Remember that elastomeric rubber's K value is higher than polyiso, phenolic foam, and fiberglass, so you're going to need relatively more thickness of this material to achieve the same insulating performance. This slide shows the same materials we just reviewed alongside their densities, service temperature ranges, and whether or not they meet 2550 flame smoke rating. Again, for PIR and phenolic, it's important to emphasize that for application on a chilled water system, you are extremely unlikely to need thicknesses greater than 1.5 inches. I won't spend too much more time on this slide. It is interesting to note the service temperature ranges of all of these materials. It gives you an idea of what other applications that they can be used on outside of chilled water systems. Also, the last column here is a nice summary of the K values and perm ratings that we just reviewed in all of the prior slides. Again, for all the materials we've covered, for application on a chilled water system, it's critical that proper thickness and vapor retarder integrity are accounted for. This chart shows a comparison of the required insulation thickness for each material on 2 separate service temperatures, 35 degrees and 40 degrees Fahrenheit, at various pipe sizes. Again, it's a way to see how the K values we just reviewed compare when translated to insulation thickness requirements. For pipe sizes less than 1 inch in outer diameter, there isn't a tremendous difference between the thickness requirements of the materials. You'll notice that you would need greater thickness for cellular glass and elastomeric rubber. However, if you look at the bottom row for the largest sizes of pipe, you begin to see more clearly where some materials will require greater thicknesses for the same application. Again, the particular environment that the chilled water system is being installed in is also an important consideration when determining insulation thickness requirements, and as such, you should keep in mind that additional thickness may be required for condensation control. With that, I'll pass it back over to Kathi.
Thanks, Meredith. Now let's turn our attention to discussing vapor retarders and jacketing. Similar to the way that PIR may sometimes be incorrectly referred to as urethane, we often hear the phrase vapor retarder jacketing used. While there are certain vapor retarder products that can also act as a protective jacketing, this is often not the case in an area of mechanical abuse, such as sometimes where a chilled water system exists. Jacketing is usually intended to serve the purpose to protect the insulation system against mechanical abuse. So let's talk first about vapor retarders. The selection of vapor retarder must be based first and foremost on its permeance. This is the rate at which water vapor passes through the product in question under some specific conditions of temperature and partial pressure of water vapor. The main purpose of a vapor retarder is to severely limit the movement of water vapor through it and thus into the insulation system. A secondary but still important purpose is to keep liquid water out of the insulation system. The permeance performance of vapor retarders is measured in units of perm, and a lower value or a lower perm rating means lower water vapor transmission and therefore superior performance. In chilled water applications, the industry recommended standard for vapor retarders is less than or equal to 0.02 perms. This helps assure the long-term performance of the insulation system by suitably retarding the entry of water and water vapor into the whole insulation system. In building and construction industry, there are many different types of materials used with widely varying water vapor permeance. You can see some of these shown here. Piping insulation, by contrast, always has a year-round unidirectional flow of water vapor. Even though there's often a driving force for water vapor flow, it's always into the pipe insulation. For that reason, and because there is no effective way to remove water that has entered a pipe insulation system, the permeance requirements for pipe insulations are much more stringent. Whereas craft paper, house wrap, or even polyethylene film might have a good permeance performance for use in a building envelope, none of these is acceptable as a pipe insulation vapor retarder. As this table shows, there are comparatively few materials with that 0.02 perms or lower performance required to be a pipe insulation vapor retarder. Among materials which do have acceptable low permeance for this application, you can see at the bottom of the chart, mylar aluminum mylar, some laminated membranes, ASJ, PASJ, and JM Sarin CX PVDC vapor retarder foams. And speaking of the last item, let's talk a little bit about JM Sarin 540CX and Sarin 560CX. JM Sarin CX vapor retarders are plastic films with outstanding performance in this application. The two products are the 540CX and the 560CX. The primary difference between these two is their thickness and the resulting permeance performance and strength. The 540CX is 4 mils thick and has a permeance of 0.02 perms, while the 560CX is 6 mils thick and has a permeance of 0.01. Both have associated Sarin XDX tape for use in sealing butt joints and for spiral wrapping around the insulation at fittings to ensure a high quality and continuous vapor retarder is applied to these locations. For chilled water applications, the Sarin X540CX is typically used. The 560CX is used more often for much colder and more demanding applications like refrigeration, very cold, and even cryogenic applications like LNG pipes. Sarin XDX film and tape meet the ASTM E84 flame spread and smoke developed rating of less than or equal to 2550, and it can be, as already mentioned, factory applied. If you would like more information about our Sarin XDX vapor retarders, you can click on the link on our website or let your local JM contact know. And finally, I'm turning the presentation back over to Meredith.
Thanks, Kathi. Earlier, when I covered fiberglass insulation, I mentioned that it is offered with two different types of factory-installed vapor retarders. There's ASJ, which is composed of an aluminum foil inner layer, reinforcing scrim, and an outer white craft paper layer. It has a perm rating of 0.02 and a puncture resistance of 55 psi. At JM, our Ultra offering is a poly-coated version of ASJ. It's essentially the same vapor retarder, just poly-coated. And that additional poly-coating provides a lower perm rating as well as more puncture resistance, both of which are attractive qualities for use on a chilled water system. Additionally, as I mentioned before, the poly-coating allows small amounts of moisture to be shed off of the insulation. Both types of vapor retarders are offered with matching tapes to help complete a sealed system, as well as to complete that clean aesthetic appearance. Outside of the perm rating, you may also want to consider some other qualities when selecting your vapor retarder. On the last slide, I mentioned the puncture resistance differs between ASJ and Ultra. And again, because a punctured vapor retarder will lead to moisture penetration of the insulation on your chilled water system, this is an important aspect to consider. Obviously, cost is something else to consider. Not all vapor retarders are created equal, so they won't all cost the same. Finally, I'll touch briefly on some different materials that can be used as protective jacketing. Again, protective jacketing can be an important consideration for a system or parts of a system that may be in an area of high traffic to help ensure system integrity throughout its life. There's PVC jacketing like JM Zeston products, which come in 2 different gauges and 14 different colors. There's also various aluminum and stainless steel jacketing that JM also offers. With that, I'll let Kim wrap up the presentation before we take some questions.
Excellent. Thank you so much, Meredith. So I do want to go over a couple additional resources that we have available to you if you're looking to install a chilled water system and you plan on using JM insulating materials. First and foremost, we have installation guides for Microlock HP and Microlock HP Ultra, as well as Trimer. And these are both for, on the Microlock HP, you'll see it has high temperature and low temperature applications. The Trimer application guide is specifically for chilled water insulation systems. So if you go to the Trimer portion of our website, if you search Trimer 2550 on our website, you will find that in the drop-down menu on that product is this installation guide. Same for Microlock HP. And then you should have also received in a chat just now a link to both of these installation guides. Now, if you're looking for more resources, either educational resources or even product resources, we do have basically our Insulation Intel Hub called The Source. And this is where we have all of our recorded webinars. We have product specifications, links to our blog, product description. So if you're looking at 2 similar products and you'd like to know the differences between them, this is a great place to find that. We also have tools like the NEMA 3E Plus tool if you're using fiberglass, and then training resources on there as well. So this is a great tool. You can access it directly from our mechanical homepage. And then also, we also have an Engineer Advisory Council, and this is basically a forum that we get together with thought leaders in the engineering industry to talk about their pain points, what they see happening in evolutions in the industry, et cetera, and how we as a manufacturer can better support engineers. And this is something we'll be hosting once the social distancing restrictions lift. And so if this is something you're interested in attending, there is a question in the survey. Simply mark yes, and we will be in touch with you when it's time to host our next Engineering Advisory Council. And then finally, for everybody who attended today, you will get a certificate of completion. This should be in your inbox by Friday, so keep an eye out for that coming your way. And with that, we are going to get to some questions. We had a variety of questions submitted ahead of time, so we're going to start with those. There are some questions that were highly specific and very application specific. And in that case, we're actually going to reach out to you privately instead of answering them live on the webinar today. So with that, I'm going to kick us off with the very first question we had submitted, which is, I'll start with you, Meredith, is how water resistant is the insulation being installed on exterior equipment?
So that's really going to depend on what type of insulation that you're using. We mentioned in the presentation that closed cell insulations have the benefit of being more water resistant, and I can let Jim elaborate a little bit more on that.
I'm kind of our technical specialist for the cold insulation area, particularly the closed cell insulations. As Meredith said, it really depends upon the insulation you're using. The first thing to remember is that the insulation resistance to water should be viewed as the backup. The main resistance to water and water vapor is provided by the vapor retarder. With that being said, in exterior, non-climate controlled environments, I think there'd be a tendency to recommend a closed cell trimer PIR or phenolic type of insulation with a good high quality vapor retarder applied to the surface. If it's exterior, you need to have the right protective jacketing. It's going to most likely be metal jacketing outdoors, and that needs to be installed and designed properly to shed water so the joints need to point away from the prevailing winds and point downwards to naturally shed the water. I think that's what I have to say for that.
Thanks so much, Jim. And my apologies to the audience. The person we just heard speaking is Jim Young. He is a technical rep here at Johns Manville, and he's on board today to help us answer some questions that are coming through. So I apologize for not introducing you sooner there, Jim. The next question we have is, which component of the chilled water line does not require insulation, and would insulation promote rust of valves? Meredith, can you kick us off here and then pass it on if you feel necessary?
Sure. So the whole system should be insulated. Any part of the system that is not insulated is going to create the opportunity for condensation. And I think you had mentioned whether insulation would prevent condensation, or if it would cause it. So essentially, if you're putting insulation on a system, you're going to prevent condensation, and that's going to help prevent rust because you're going to basically eliminate the effect of condensating pipes.
All right, thank you. The next question is for you, Kathi, and that is it okay to use wood blocks for supporting the pipe?
Thanks, Kim. Well, we wouldn't normally make a recommendation to use an item like a wood block when there is definitely an opportunity to support the pipes in a better way. We have the Trimer rigid insulation in a variety of different densities and strengths, and we routinely help different specifiers and contractors with pipe support calculations. So in those cases, we actually can help determine what grade of Trimer to use at the pipe supports. We would never really recommend wood blocks, and I think there's just better design opportunities to use a properly calculated and fitted pipe support or saddle.
All right, thank you, Kathi. The next question is, I'll start with you, Meredith, and that is, how important is the vapor seal on a chilled water system?
So it's very important. We've talked throughout the presentation that a sealed system with proper vapor retarder integrity is critical to preventing moisture drive into the insulation. So very important. If Jim wants to elaborate on that any more, I'll let him speak to it.
Hi, this is Jim. I actually want to go back and just mention something about a previous question. Somebody asked what parts of the system need to be insulated, and Meredith or Kathi, I don't remember who it was, said the whole thing. And that's absolutely true. However, I will say that there are times when something isn't insulated or can't be insulated, or maybe a valve is getting constant maintenance, so they choose not to insulate it and accept the condensation that's going to likely occur on it. When that happens, when you have a section of any cold pipe, be it chilled water or something colder that is not insulated, you need to terminate the insulation on either side of that bare area with a vapor stop or vapor dam. That's really important. So I don't have anything to add to this question, but I felt that was worth bringing up the previous question for.
All right, thanks, Jim. The next one I'm actually going to direct to you, Jim. So that is how to best ensure vapor barriers around items such as hangers, supports, and valve handles. Okay. This is a really important question, and it comes back to what Meredith and Kathi were talking about. The continuity of the vapor retarder is critical to the success of the insulation system. And so you want to maintain that continuity around all your supports, hangers, etc. The first thing I would recommend is to use external supports. So use pipe supports that do not pierce the insulation system. Use a pipe support that the entire intact insulation system rests upon. So you don't have any kind of penetration and no need to worry about sealing a penetration. All right, that's all nice and easy to say, and yet we sometimes have the necessity to have penetrations. Maybe you have a vertical run of pipe that has to be supported internally. There are certainly valves in the system, and every valve is going to have a valve stem of some sort that most likely penetrates the insulation and vapor retarder system. So I would say that you want to try to insulate around it, vapor retard around it, and then seal around whatever the penetration is with caulking. Any kind of seal around a penetration is a weak point. And so again, it's best if you put a vapor stop or vapor dam on either side of these weak points. So if you have a valve, terminate your insulation on either side of it, and then insulate the valve. Get the vapor retarder as continuous as possible, seal around the valve stem, and then this is very often overlooked, especially with chilled water that's in hidden spaces of buildings, but a good inspection and maintenance program is important. A periodic inspection of known weak points like penetrations is important, and repair of damage to the vapor retarder, or even if it's not damage, if it's just a place where it's pulled loose from a valve stem or something, that kind of area can be repaired. All right, thank you, Jim. To put you on the hot seat again, the next question is, can you please discuss the factors used to determine the thickness recommendation and benefits of going thicker when necessary?
Well, the factors that determine the thickness there's a lot of them. I mean, the simplest one, and it's even complex, is the thermal conductivity of the insulation. And Kathi and Meredith talked about that. Certain insulations are better insulators than others, and they require less thickness. Phenolic, in the ones we discussed today, phenolic and PIR the least, cellular glass the most, with fiberglass in the middle. So that's the simplest one, and it's still complicated. The other factors that influence the thickness required, well, let's start with the energy codes. Those are sort of a de minimis level. You need at least those just to comply with the codes. Usually, though, if you achieve condensation control, you're going to get the code required thickness. So usually, we also are looking to get condensation control out of the insulation, and the thickness for that, the thickness required for that, is also going to depend upon the climatic conditions. Indoors, in a climate-controlled space. So if you've got pipes within the air-conditioned part of a building, you're generally going to not have very harsh conditions. You're going to have somewhere in the 70 to 80 F range, and you're going to have roughly 50% relative humidity. Glass fiber is a great choice in these applications. If, on the other hand, you get into parts inside of a building which are not climate-controlled, like machine rooms, sometimes vertical pipe chases, penthouses, things like that. Not the kind of penthouses where rich people live, but another kind. Those will not be climate controlled, and certainly outdoor applications are not going to be climate controlled, and you're going to want to adjust your thickness to account for that. There are tools that are used. 3E Plus was mentioned. JM also has internal calculators that work better for the trimer and phenolic materials to determine the required thickness based on all those factors, including pipe size, which I didn't mention. So all those factors together and some others I didn't mention go into the calculations to determine pipe size. And I won't get into the details here, but JM would be happy to work with anybody who had questions about pipe sizes. We can create pipe thickness tables or create thickness recommendations for your specific application. Go ahead, Kim.
Thank you, Jim. And I'd just like to add a quick note on the end of that. The NEMA 3E Plus tool is great if you're using fiberglass. If you're using any of our foam insulations, primer, the supercell, please reach out to us directly. We can get you. NEMA 3E Plus is not ideal for the trimer materials. So just something to keep in mind as you're establishing insulation thicknesses for your systems. The next question is for Meredith, and that is, what is the life of moisture wicking insulations?
So I believe that this question is referencing a type of insulation product that OC used to offer, which was a moisture wicking fiberglass insulation. So JM has never offered a moisture wicking fiberglass product, and that product was discontinued by OC. I would guess that the reason why it was discontinued is because it's really not a good idea for insulation to get wet. If water enters an insulation system, it's going to increase its thermal conductivity. So I can't speak to the life cycle of it, and I'm not aware of any existing moisture wicking products that are available today.
Excellent. Thank you, Meredith. The next one is for you, Jim, and that one is, can you discuss the regions of extremely cold weather where temperatures can fall down to minus 50 degrees?
Sure. I think that I'm going to interpret this question maybe a little differently. I hope it's what the asker intended. I think if you're talking about ultra cold climates like that, you're probably concerned about freeze protection. And so maybe you've got a Edmonton, Alberta sort of location where in the summer you might have to worry about condensation control and heat gain, but in the winters maybe the pipes are going to be exposed to minus 50 degrees and you have to worry about the chilled water freezing. So I think that's the way I'm going to interpret this. The most important thing to note is that insulation does not stop the flow of heat. It only slows the flow of heat. What that means from a freeze protection point of view is that no matter how much insulation you put on a pipe, it cannot prevent freezing forever. It can only prevent freezing for some certain amount of time. So the best way to handle this in an extremely cold climate is through proper calculations. If it's a flowing pipe. So if you've got a flowing pipe, JM can help with calculations of a temperature change in a flowing pipe to make sure that the water, as it maybe goes from one building to another outdoors and sees that minus 50 degree environment, that it won't freeze in the amount of time that it is exposed outdoors with the insulation thickness that's on it. And we can tell you what insulation thickness would be necessary to give you certain time to freeze. If it's a quiescent or stagnant water in a pipe, then you have a totally different situation. There's no amount of insulation, of any kind of insulation, that's going to prevent freezing forever. So you have to start thinking about heat tracing the pipe. So you have to put heat tracing on there. That's something that JM can help with a little bit. We aren't heat tracing experts, but if someone tells us the amount of heat that is coming from the heat tracing, we can balance that against the heat loss through the insulation system and tell them an insulation thickness necessary to balance, to get that balance and hopefully then achieve the freeze protection. One other thing to note is that for heat tracing, whether it's electrical or much more rarely like a copper tubing type of heat tracing, containing a heated glycol or something, it sometimes is necessary to modify the insulation to accommodate this electrical or copper tubing type of heat tracing. It's too complex to get into the details of that here, but just note that you may have to work with your installation contractor or the fabricator, and JM can help also with the options for how to put the insulation around a pipe with heat tracing on it. Go ahead.
Excellent. Thank you so much, Jim. The next question is for you, Kathi, and that is, can you talk a little bit about how the blue stuff, and I believe that's referencing our XPS PIB product, compares to Trimer?
Sure. Basically, the XPS PIB, or what people often refer to as styrofoam, is not a product that would be used in a commercial building chilled water application due to its flammability issues. But XPS PIB styrofoam is really the most popular insulation in refrigeration applications, and I guess that might be a good topic for a future webinar.
All right, thank you so much. Meredith, the next question is, can you cover the aspects of suitability of elastomeric rubber as insulation of chilled water systems?
Sure. So we did talk a little bit about elastomeric rubber or rubber earlier in the presentation, and the point that I think is most important to note with that type of material is that you need to put a vapor retarder on it if it's going to be used on a chilled water system. Again, the material itself doesn't have the appropriate perm rating, that 0.02 perm rating that you're looking for use on a chilled water system. So you need to make sure that a vapor retarder is used if you're going to be using elastomeric rubber on a chilled water system.
Great, thank you. And I do notice we are 1 past the hour, so just so everybody's aware, we'll continue to answer these questions up until half an hour past, and then at that point we'll reach out to anybody whose questions we didn't get to. We'll reach out to you directly. So with that, we'll continue on to the next question, which is also for you, Meredith, and that is, how do I get the insulation?
So you can reach out to us, and we will put you in contact with your local market development manager that can identify what distributors are available in your area to purchase insulation, and the particular distributors that we work with at Johns Manville. So really just reach out to us, and we will put you in contact with the right person.
All right, thank you.
Hey, this is Jim Young. Let me just expand on that just a tiny bit. More often than not, you're going to not buy the insulation. You're more likely to be hiring an insulation contractor to do the work, and the insulation contractor is going to buy the insulation. So JM can also help point you to some insulation contractors in your region, to the same contacts that Meredith said, but just don't think that you have to necessarily buy the insulation, although it certainly is possible. More often, the insulation contractor that's hired will be buying the insulation from the same fabricators that Meredith mentioned.
All right, thank you. That's a good point, Jim. So the next question is, can you discuss insulation applications specific to winery and brewing applications? So Meredith, can you kick us off on the fiberglass side, and then maybe Jim and Kathi can bring up on the Trimer side?
Sure. So if you're going to be using insulation on either a brewing application or a winery, you might encounter some different service temperatures besides what you would encounter on a chilled water system. So I would comment that fiberglass is an excellent insulation to use on the hot side. So our fiberglass pipe and some of our fiberglass boards are rated to up to 850 degrees. So they would be great materials where you're looking at a higher service temperature. And if Jim wants to elaborate on the cold side.
Sure. Well, the first thing to note is that I think some field trials are necessary here. We definitely need to visit some wineries and brewing locations. Okay, but as Meredith said, just saying winery or brewing doesn't really tell you the whole story. I like to say that the insulation doesn't know what's inside the pipe. It only knows the pipe temperature and the climate around it. So it doesn't matter if it's wine, beer, or radioactive nerve gas inside. The insulation is designed based on the temperature of the pipe, the size of the pipe, the climate. So there's really not much difference between a brewery and a winery and refrigeration or chilled water. It just depends on which pipe temperatures you're talking about. Since Meredith already answered on the hotter side, I'll say that on the colder side, if this was in the 30 to 50 degree F range, then it would, all the things we talked about today related to chilled water would directly apply. And our trimer in chilled water or styrofoam in chilled water installation guides would be applicable. If this was colder, and I certainly would think that could be possible, we would probably suggest that you refer to our refrigeration installation guides for styrofoam and trimer. There's a few more details that are required in refrigeration applications because they're colder than for chilled water. But the key thing is, continuous vapor retarder, high quality insulation, proper jacketing. I will say that oftentimes, not always, but oftentimes, wineries and breweries are also showcases. Some of them are just working facilities. Some of them are showcases. I'm in Western North Carolina, and the Sierra Nevada Brewery is near here, and it is absolutely a showcase. Most impressive brewery I've ever seen. And in a location like that, they're looking for extremely beautiful insulation systems on their pipes because they've got tours going through and looking at it. So multiple color-coded PVC systems or oftentimes stainless steel jacketing is being used indoors, which is not very common, but it might be used in a brewery or something like that where it was a showcase. But in general, I think the same, I won't say rules, but the same recommendations for chilled water and refrigeration would apply depending upon the temperature of the pipe in the brewery or winery.
All right, thank you, Jim. The next question, Meredith, you can kick us off with fiberglass, and then we can take it over to Kathi and Jim again. And that is, what is the life cycle of insulation due to R-value deterioration?
So for fiberglass, there's really not going to be a deterioration in the R value over its life cycle. The insulating value that you get in fiberglass is due to the air pockets in the material, and that doesn't really degrade over time. So there should not be a significant reduction in the R value for fiberglass during its life. And I can let Jim speak more to some of our closed cell options.
Sure, thanks, Meredith. The thermal conductivity values that we report and that are contained in the ASTM documents for PIR and Phenolic, those are already aged values by rule. There's various laws about this as well. So we're very conservative in both the aging of samples before testing, as well as we report conservative values. Just as an example, the 0.19, which is sort of the representative number for PIR, is an aged value, but we have actual testing of aged values, of aged PIR with a 0.167. So we want to use the 0.19 for design purposes, just to be conservative. So there really isn't going to be significant degradation of the thermal conductivity beyond the values that we're already using for design purposes over the lifespan of the insulation for any of the JM closed cell products.
Excellent. Thank you, guys. Jim, I'm going to start with you on the next question, and that is, do you recommend painting chilled water piping prior to insulating to mitigate corrosion issues? If so, what product would you recommend? Epoxy paint, primer, etc.?
Okay, this gets at the whole corrosion under insulation issue. Very, very complex, lots of stuff on it. JM has a couple of letters, general letters, and a tech data sheet on this subject to which I can refer you as well. But I'll say in general that insulations of all types get I think, an inappropriate bad rap for causing corrosion under insulation, or CUI. what really is the source of the corrosion is water that gets into the insulation system. So the first way to prevent corrosion is to keep water out. If water does enter, people get worried about there being nasty ions in the insulation or something like chloride ions that could exacerbate the corrosion. But if water's getting in, it's coming from the environment, which is just an inexhaustible source of nasty ions, including chlorides. So the real key is to prevent water from entering the system, which is easy to say and hard to do. You need, closed cell insulation works really well. High quality continuous vapor retarders work well. And then you also, if water is going to still get in, and this is something you have to the designer, the specifier has to make the decision on how much effort they want to put into the quality of the vapor retarding and insulation system. If you are still worried about it, then you can coat your pipes with corrosion inhibiting coatings. Now, since we're talking about chilled water today, I think it's reasonably safe to say that the vast majority of the piping is going to be carbon steel, not stainless. So with that in mind, you can either paint the pipe or you can use one of the corrosion inhibiting gels. There's one called a blue goo. That's not like the official name, but it's often referred to that in the industry. That's suitable for use on carbon steel pipe. I don't believe they have any evidence that it helps with stress corrosion cracking of stainless steel, but for carbon steel pipes, that can play a role. There's also a temperature issue, and this is really important and too often overlooked. Corrosion under insulation occurs in a temperature range. For stress corrosion cracking of stainless steel, that range is about 140F to 250F. And for carbon steel, it's about 32F to 250F. If you're above the temperature range, water can't reach the pipe. It boils off before it gets there. If you're below the temperature, and the colder temperatures differ depending on if it's stainless or carbon steel, 140 for stainless, 32F for carbon steel. If you're below that temperature, the chemical reaction of corrosion is slowed to insignificance, so you don't really have to worry about it. But since it's chilled water, you're going to be in the range, and since we're assuming carbon steel pipe, you're going to be in the range where corrosion is a concern. So you take a multi-tiered approach. Keep the water out, good quality continuous vapor retarders, and if the specifier deems it necessary, they could coat the pipe with either usually a multi-part epoxy or the corrosion inhibiting gels. Go ahead, Kim.
All right, thank you so much, Jim. So the next question we have is kind of the great question we've had a lot of times. And Meredith, I'm going to hand this one to you. And that is, for chilled water applications, do you recommend Trimer or fiberglass?
Well, it depends is really the answer. It's really going to be very dependent upon the particular environment and conditions of your application in terms of, whether one is better versus the other, or it depends on what your priorities are. If your, fiberglass is oftentimes a lower cost option, so if that is a driving priority, that needs to be considered. If it's very, very important that system integrity is maintained, or if there's concern about needing more moisture resistance, a closed cell option like PIR might be more appropriate. So there's really not one good answer. It's going to be dependent upon the specific context. Jim, would you add anything else to that?
It's like your children, right? We love you both equally. But no, Meredith is exactly right. It really depends, I believe, on the climate. But Meredith's got a good point. There are people for whom the cost is paramount. If someone's building a building for sale, building a strip mall for sale, and all they care about is that it lasts a year till the warranty's up, and then they're just looking to sell the building, fiberglass is probably the right choice. For an owner-occupied building, like governments, schools, museums, things like that, if it's the climate-controlled portion of the building, I think fiberglass is probably the better choice. But if it's the non-climate-controlled portions, where you need the extra water resistance is going to give you system longevity. My personal recommendation would be, and certainly outdoors, would be to go with a closed cell insulation with a high quality vapor retarder on it. So it depends is with the elaboration is the right answer.
All right, thank you both. Meredith, the next question is, do you recommend using PVC outdoors, and is it UV stable?
So PVC, the white PVC has a UV resistant component, so it would be okay to use our thicker gauge white PVC. We have tested it for that UV resistance outside. It would not be appropriate to use any of our colored PVC because it does not have that TiO2 component, which provides that UV resistance. So you got to make sure that you use the right kind of PVC, which would be the thicker gauge white, could be used outside.
All right, thanks.
Elaborate a little bit. I would say that's probably correct. I will say that there's not a lot of PVC used outside, but we want to distinguish one thing here. Outside, the way Meredith was saying it and the way I mean it is sunlight exposure. If it's like in the parking garage where it's completely protected from the sunlight, but it's technically outdoors, I think PVC would be fine. In sunlight exposure, you have to be a little more concerned with the things that Meredith is saying. Metal jacketing is much more commonly used outdoors or in sunlight exposure. And there's a significant drawback to metal jacketing compared to PVC, which is its emittance. The low emittance of aluminum jacketing of 0.1 compared to the high emittance of PVC at 0.9 can lead to a requirement for substantially greater thicknesses of insulation for condensation control. If that becomes a concern, metal jacketing is readily available from JM with painted outer surfaces. So you can get a white painted, aluminum jacketing, which will eliminate the drawback of the low emittance of the aluminum and how that could lead to high insulation thicknesses being required.
All right, thank you. Jim, if you could talk about this next question, that would be great. And that is, how do required thicknesses change for outdoor applications?
I missed a word. How do what thicknesses?
Required thicknesses.
Oh, okay. How do required thicknesses change for outdoor locations?
Correct.
Okay. We've kind of talked about this. Everything's a situation. There is no hard and fast rule. You really have to do the proper calculations for every situation. The thickness requirement in Houston outdoors is going to be different than in Las Vegas outdoors. And it depends upon a variety of factors. Let's start with the insulation material being used. And we talked how different materials have different thermal conductivities. That's one aspect of driving the thickness. The next would be the design criteria. Is it code compliance all you care about? Maybe in Vegas that's all you care about because it's never humid enough to worry about. Or maybe that even in Vegas there's a desire to achieve some degree of condensation control on the few times a year that it's humid there. So you'd have to select your design criteria. Is it code compliance only? Is there a heat gain limit? Is it condensation control? And then you have to start examining the climate and the pipe size. So all of these things are understood in the industry. They're not rocket science, but they do involve calculations. JM can help with this, and they do involve understanding of specs and climate conditions for different locations. So JM can definitely help anybody who has questions about this for either general needs like a thickness table or for a specific project. If someone's writing a spec for a specific project, we can help them consider these factors and come up with the appropriate thicknesses for the maybe multiple insulation products they want to use on that project.
All right, thank you, Jim. Kathi, this next question is for you, and that is the Sarin vapor retarder stretchable around elbows?
I'm not sure what they're referring to as stretchable, but it is very flexible. So while you wouldn't be like tensioning the material, you would, it would definitely easily be wrapped around any, round or cornered surface. And again, we have the tape that would be used, to help with any portion of the system that needs to be, sealed together with the vapor retarder if there was an odd shape or the butt end joints and that sort of thing. So yes, that product can definitely be used around a variety of shapes in conjunction with the tape. And I don't know if Jim has anything to add to that.
I would say that if it's an elbow specifically, most likely the best way to do it with the Sarin X tape would be to spiral wrap the appropriate width and thickness of tape depending upon the elbow size. Well, not the elbow size so much as the outer insulation elbow size. We have 1, 2, and 3 inch width tapes in 2 different thicknesses, and those can be spiral wrapped around the fittings and elbows to achieve a continuous and high quality vapor retarder at those locations.
All right, thank you, Jim. This next question I'm also going to send to you, Jim, and that is, can I use Sarin X around fiberglass over the ASJ jacket?
Yes. Short answer is yes. Before you did that, I would question why you wanted to do it. Sarin X is, you would not do it for appearance purposes. ASJ is going to look better than Sarin X. Sarin X is not the most aesthetically pleasing jacket in the world, vapor retarder in the world. It often has some wrinkles and things in it. So I don't think you'd do it for aesthetics. And it's still a plastic film, so you'd also would not do it for physical abuse resistance. You'd want to use PVC or metal for physical abuse resistance. So if you were, the only reason you'd really be doing it would be to get a better quality vapor retarder than good old ASJ. And if that was your goal, maybe you ought to be ordering your fiberglass with a plasticized ASJ, which is, I think, substantially superior to standard ASJ. But bottom line, if someone wanted to do it, yes, they absolutely could buy rolls of the fiberglass or pre-cut sheets to the right size with self-sealing lap on them, and put that around any vapor retarder, including ASJ.
All right, thank you. The next question is for you, Meredith, and that is, does the tape come in colors other than white?
So the tape that is used on our fiberglass pipe is really only offered in white because it's intended to match the vapor retarder that is on the fiberglass pipe section. So there's there's tape that's offered that is basically the same facing, which has that white craft paper layer on the outside of the tape, so it's an exact match to the ASJ vapor retarder. And then there's also tape that has the poly coating on it to match the ultra vapor retarder. But otherwise, I am not aware of it being offered in other colors. There is more on the HVAC side for duct wrap, which we make a black duct wrap. We do offer a black tape that goes with that product, but at that point in time, we're talking duct wrap, not fiberglass pipe.
All right, thank you.
I would add that for Sarin X vapor retarder, the tape only comes in white to match the film.
All right. Along the line of aesthetics is the next question as well, and that is there a paintable jacket material that you would recommend for exposed installations that will be painted to match surrounding areas? For example, exposed structure painted black in an office area. Meredith, can you start there, please?
So we would never recommend that you paint the facings on our pipe insulation because we don't know what that does to the flame smoke rating. Paint can serve as a fuel source. So because we don't know what type of paint is being used, you're going to void our manufacturer's warranty by painting that insulation. So we would not recommend that you paint it. A good alternative, if the application is inside and you're looking for a particular color aesthetic would be to use PVC jacketing on pipe insulation so that you achieve a certain color aesthetic. I had mentioned in the presentation that it's offered in white and then 13 other colors. And then I had just mentioned in the prior question that on the HVAC side, we do offer duct wrap in both a black and a white PSK facing.
All right, thank you. Jim, the next question is for you and me. So I'll kick us off and then I'll toss it over to you. And that is, where do we find the condensation control software for insulation thickness? And if you want to find it for Fiberglass, you can download it on the source, as I talked about here. And that is, you can find that from the mechanical page on our website. If you go to tools, you'll be able to download the 3E Plus tool to determine your insulation thickness. If you're using Trimer or Trimer 2550 or Supercell Phenolic, we ask that you reach out to us. Jim, if you could talk about that a little bit, that would be great.
Sure. The 3E Plus tool is uses the ASTM C680 calculation methodology for determining insulation thickness. And C680 is the right thing to use. But you have to have a software system that uses that methodology. And the 3E Plus is one of them. But 3E Plus is not ideal for closed cell insulations made with blowing agents, like the Trimer PR and the Phenolic. So we have a internal tool that we use for those products to determine the proper insulation thickness. I would add one other caution about 3E Plus. Excuse me. Buried in the software of 3E Plus for condensation control is a 0.75 degree F safety factor. This is not really published anywhere. So when you ask 3E Plus to do a condensation control calculation, even for fiberglass, it's not going to give you the thickness needed to get your surface above the dew point. It's going to give you the thickness needed to get your surface, your outer surface, above the dew point plus 0.75 degrees F. 0.75 degrees F may not sound like a lot, but when you're talking about insulation thickness to raise that outer surface temperature, it can make a difference. I've not done any chilled water calculations, but in refrigeration, like at around -40 or so, it can change your thickness from 4 inches to 5.5, that 3/4 of a degree safety factor. So I wouldn't be surprised if it could change your insulation thickness for chilled water by 1/2 inch. Maybe 1 inch is what you really need, but the 3/4 degree safety factor might get you to 1.5 inches. Two things, fortunately. One is the owners of the 3E Plus software are aware of this and are working and have said they're going to address this in the next version. But for now, that's not available. So the other good news is that in the table of results that you get when you use 3E Plus, it tells you the dew point and it tells you the surface temperature as a function of insulation thickness. It also puts a gray bar across the insulation thickness that gives you the condensation control with that 3/4 degree safety factor. But you can manually go in and look at it and say, okay, that's what it says, but where does my surface temperature first exceed the dew point, not including the 3/4 degree, and you can very quickly, in the same table that you're looking at your gray bar result, you can just look up a couple lines and see what the thickness is that is necessary without the 3/4 degree safety factor. You just have to be aware that that's there, and I recommend going that route. And then contact JM with questions about the closed cell insulations, and we can run very quick and easy calculations for using our internal software that work better for the closed cell insulations. Thank you, Jim.
The next question is, will you provide presentation material at the end of the presentation? We will send you an email, everybody who attended. Once we recorded the webinar today, we'll send you an email once it's live and posted online for you to watch on demand. So the next question is also for you, Jim, and that is, what do you recommend at expansion or flexible joints?
Okay, that question can mean different things. It sounds like they're asking about where the pipe has an expansion joint or a flexible joint, and not an expansion, what's called an expansion contraction joint on the insulation, which is a totally separate question. Both are good questions, but I'll answer the one that I think they're asking, which is what do you do at an expansion joint in the pipe? That's a tough one. I think you work closely with your contractor to figure out how to maintain your vapor retarder integrity or continuity across that. The problem is that the vapor retarder, or excuse me, that the pipe may expand and contract, the insulation might move, and you need to have a way to maintain that vapor retarder continuity even in light of the pipe and insulation moving. It might be a good place to put an insulation expansion contraction joint. It would really depend upon the style of pipe expansion contraction joint. So I think that's probably more a case of talk to us, we'll work with you and your insulation contractor, and we can come up with an appropriate way. But the most important thing is to maintain your vapor retarder continuity across that location.
All right. Thank you, Jim. Well, it is 1:30, so we are going to wrap it up here today. If we didn't get to your question, we will answer you privately in an email. And with that, we thank you all for your time. We hope you're staying safe and healthy and that you'll join us in the next month for our next webinar. So take care, everybody, and have a great rest of your week.